All right, welcome to the chapter 2, part 5 video. We started it in class. We did actually most of it in class, and we're just going to apply families of functions and looking at kind of the translations and also looking at all of that in the context of absolute values. So remember, we did our project on absolute values, trying to understand absolute values and inequalities a little bit more. And we are going to kind of take a deeper dive again into absolute values from the graphic or the visual perspective, okay? So let's think about this. You're jogging at a constant speed and your jogging route takes you across the county line. So suppose you graph your distance from the county line with respect to time. What would the graph look like? Okay, so let's think about where we started our route. And no matter where we started our route, we were some distance away from the county line, right? So if we look at our axes here, whatever distance we started at, let's just say it's this distance, okay? So that's how far away we started to the county line. And then we're jogging and we're jogging and we're jogging closer and closer to the county line, right? And we're getting closer and closer to the county line. And then at some point we will get to the county line and we will cross the county line, right? However, as I keep jogging, I'm not getting a negative distance away from the county line, right? I am once again jogging away from the county line. And therefore, the distance is getting farther and farther away until we stop jogging, right? Well, notice this is a V-shaped, and because it's distance, and distance is never negative, this models an absolute value function, okay? The slope of this line is dependent on how fast you're jogging, so the speed that you're jogging would be the slope of the line. And then the bottom of this, this V shape, that's called the vertex. So the vertex, or the bottom of the V shape, where it turns around, is when the distance from whatever we're measuring is 0. So in this case, it's when we crossed the county line. Okay, so let's take a look at a little bit more detail into these absolute value functions. So we said an absolute value has those absolute value bars around it. And remember, that's directly above the enter or return key. If you hold shift, you should be able to type in those absolute value bars. And the absolute value parent function, so we talked about this in class, the parent function is the one that determines the shape. So for a line, it's f of x equals x. For an absolute value, it's f of x equals the absolute value of x. So those absolute value bars are what tell us the shape is going to be V-shaped. The bottom, the point of the V, is called the vertex. And because it's a V-shaped, well, that wasn't a very good V, but because it has that V shape, there is a line right down the middle of the V that we could fold it perfectly in half. And that's called an axis of symmetry. So if you remember from Algebra 1, you might recall that a U shape is called a parabola. It's when we have x squared, and that also has an axis of symmetry. It has a line where we could fold it. So some functions have this type of axis of symmetry, and the absolute value is one of those functions. So if we look at our key concept here, absolute value parent function is called f of x equals the absolute value of x, and it takes any negative number and it makes it positive. And so if we have -3 and we take the absolute value of it, it becomes +3. If we take -2, the absolute value of -2 is +2, and so on and so forth. And so if x is already positive, f of x just equals x, right? If x is already positive, the absolute value function doesn't do anything. If x is negative, it turns it positive. So it's the opposite of x. And so we can say the absolute value of a negative number is the negative of that number. So negative of -3 is what gave us the +3. right? So if I have an absolute value of a negative number, I have to double negative it to make it positive. And so we have this function notation where we now have to write it as two separate pieces. And so this is called a piecewise function. And we can write our absolute value function as a piecewise of linear functions. So we can make our absolute value out of lines, essentially. Okay, so let's look at an example. We want to graph the absolute value of x minus 4. Notice the 4 is outside of the absolute value bars. So remember in class we were saying that if we're multiplying or adding inside of the parent function, that's going to be a horizontal translation or a horizontal, we didn't cover horizontal stretches, but if it's multiplied inside, it would stretch sideways instead of vertically. So if we're adding or subtracting inside of the absolute value bars, then we would be shifting side to side. The minus 4 is outside of our parent function. It's outside of those absolute value bars, so that shifts up and down. So are we going to go up or are we going to go down? Well, the minus 4, remember vertical transformations do what they say. Minus 4 goes down by 4. So this is going to be a down by 4 transformation. How is it different than the graph of the parent function? Well, I just kind of spoiled it. So let's try graphing this function. So when x is 0, absolute value of 0 is 0, minus 4 is negative 4. Gives us this point here. When x is 1, the absolute value of 1 is 1, and 1 minus 4 is negative 3. When x is, I'm going to skip. I'm going to go straight to when x is 3. The absolute value of 3 is 3. 3 minus 4 is negative 1. So we have this arm of the absolute value function that continues going up. But what happens when I put in a negative number? So what happens if I put in negative 1? Well, the absolute value of negative 1 is 1, and 1 minus 4 is negative 3. So notice this is not continuing on in the line that we would have expected, right? It turns, and it turns because of that absolute value. And so this one will also go off, but it goes with a negative slope. So if I substitute negative 3, the absolute value of negative 3 is 3, and 3 minus 4 is negative 1. So the absolute value of negative 3 minus 4. I'm substituting that value for x, right? So 3 minus 4 is negative 1. So how is this different than the parent function f of x equals the absolute value of x? We already mentioned that it shifts down by 4, right? I'm going to just kind of sketch real quick here. That's approximately the absolute value function. So it shifts down by 4, but what else is different? If you look at these two graphs, notice the blue one never crosses below the x-axis. The red one does. And so we can say that because this shifts down by 4, we can have negative y values. Whereas the original absolute value function, the parent function, doesn't have any negative y values. So it is possible to have negative values when I'm dealing with absolute values, but only when I'm subtracting outside of that absolute value. I can never have the absolute value of something be negative, but I can subtract from an absolute value to get negative numbers. Okay, let's look at our next question here. So this is summarizing all of the different transformations that we can see for our absolute value function. So this table should look familiar. It's very, very similar to the one we looked at in class, except for this one is specific to the absolute values. So vertical translations, remember we said vertical is outside of the parent function. Outside. So when k is plus or positive, it goes up. When k is negative or subtracted, it goes down. Okay, if it's inside the parent function, then it goes sideways. And so sideways, horizontal transformations do the opposite of what they say. X minus h goes to the right. X plus h goes to the left. And that's because we want the value that would make x minus h equal 0 is a positive h value. And the value that would make x plus h 0 would be a negative h value. Whoops. Okay. For our vertical stretching and compressing, same rule applies. If I'm multiplying by a number greater than 1, it's a stretch. If I'm multiplying by a proper fraction, it's a compression. So this would be fractions, 1/3, 2/5, 7/8, and so on. And then the way that we can handle negative coefficients is by a reflection. This is negative outside is vertical. For a vertical flip, that's over the x-axis. If I have a negative x value, negative is on the inside, then I'm flipping horizontally, and that is across the y-axis. If I reflect over the y-axis, that changes my x value. If I reflect over the x-axis, that changes my y value. Okay, so we can generalize this. We can say y equals some coefficient a times the absolute value of x minus h, which shifts sideways, plus k, which shifts up and down. And then we can say our vertex is going to be the point. It started at the origin, right? For the absolute value function, we start at the origin, but then it can shift sideways and up and down by h and k, which leaves our vertex at the coordinates h comma k. Now, hopefully this is a little bit familiar because this is exactly the same way that we find the vertex for a parabola. But if you don't remember how to find the vertex of a parabola, that's okay. We're going to be applying this same thing to quadratic equations later on in the semester. Okay, and then the axis of symmetry, remember it was a V shape. The axis of symmetry goes right up and down through the middle. So if our vertex here is h comma k, then our line of symmetry goes right down through that x value. So our line of symmetry is x equals h. Okay, let's look at an example. Which of the following is the graph of y equals the absolute value of x plus 2 plus 3? Okay, so we have to know what's going on, and don't use your calculator for this. I want you to use the transformations we were just talking about. So first we identify where's the parent function. It's those absolute value bars. What is happening inside of the absolute value bars? We have a plus 2. So plus 2, what does it do? Does it go up and down, left and right? It's inside. Inside goes sideways, okay? So the x plus 2, I want to know what value makes it 0. X would be negative 2. So h is negative 2, right? The x coordinate of our vertex, it moved left. This moved to the left by 2, okay? Next, let's look at this plus 3 on the outside. Plus 3 on the outside, outside does what it says. plus 3 will go up 3. So k equals 3, it went up by 3. So that's how we can use hk to find the vertex is -2, 3. So which one of these has a vertex -2, 3? That is graph D, -2, 3. Okay, let's look at, can we determine what the formula or the equation would be for these other graphs? So here I went left 2, so it's going to be the same inside, x plus 2. But this one went down by 3, so that would be a -3. Graph B went to the right by 2, so instead of a plus 2, that should be an x minus 2. But then it also went up, so that's a plus 3. Graph C went to the right as well, so that's absolute value of x minus 2. And then it went down, so that's a -3. And then we have our answer, which is to the right, or to the left by 2 is x plus 2, and then up goes plus 3. Okay, so try this. I want you to try this, and then we'll go over the answer together. Okay, so let's start by just making some points. Notice there's no addition or subtraction at all. That tells me that my vertex is going to be at 0. I always want to start with the number that makes my parent function 0. So what makes absolute value of x 0 is 0. So let's start at 0. 1/2 times the absolute value of 0. 1/2 times the absolute value of 0 is 1/2 times 0. Anything times 0 is 0. So 0, 0. What about 1? 1/2 times the absolute value of 1. Absolute value of 1 is 1, so 1/2 times 1 is 1/2. I don't really want to graph a fraction, so instead of 1, let's try 2. 1/2 times the absolute value of 2. 1/2 times absolute value of 2 is 2, so that gives us 1. 2, 1. Do you notice anything? Hopefully you're starting to say, oh, rise 1, run 2. So let's try 4. 1/2 times the absolute value of 4. Absolute value of 4 is 4. 1/2 times 4 is 2. Oh, it worked. Okay, so here is going to be approximately my line. Okay, what happens if I put in negative numbers? Remember, we always want to try positive and negative numbers. So notice 1 didn't work. Do you think -1 will work? Probably not. Let's see what happens. So -1. 1/2 times the absolute value of -1 is 1/2 times 1, which is a fraction, so I don't want to do that. Let's try something else instead. Let's try 2, or -2. 1/2 times the absolute value of -2 is 1/2 times 2, which is 1. So notice what happened is that my absolute value function turned into a graph with a slope of 1/2. Okay, now there's a reason this happens. If I have y equals 1/2 x, it would just keep going like this, right? It would keep going like the blue line. However, once I take the absolute value of x, I take all of those y values and I turn them positive. So it's basically a reflection to make all of the y values positive. All of the y values that used to be negative are now positive, okay? And so this honestly is a line with a slope of 1/2. However, it's V-shaped because at some point I said where all of the y values have to be positive because they're distances. And that's why an absolute value function is V-shaped. Okay, let's take a look at our next one. We're almost done. Without graphing, what are the vertex and axis of symmetry of the graph of this function? And how is the parent function transformed? Okay, so I want you to think back. We talked about A, H, and K. I'll write the formula here. Y equals A times the absolute value of X minus H plus K. Can you tell me what the vertex is and how it has been transformed? And then we'll go over it together. So let's start with H and K. H, X minus 2, so H is 2, plus 4, that means K is 4, and there was a times 3, so A is 3. So the vertex, remember, is H comma K, so that's 2 comma 4. That's how we can find the vertex. We didn't even need to graph it, okay? And how is it transformed from the parent function? It is moved to the right. Oops, let's try that again. Moved right 2 and up 4, right? In order to get to the point 2 comma 4, we've got to go right 2 and up 4, and slope of 3. So this is steep. We can say this is a vertical stretch by 3. Okay, so without having to graph it, and you can always check it on your calculator, but remember, we're also working on efficiency. So the more time you spend typing things into and double checking on your calculator instead of being confident in your algebraic skills, the more time you're going to waste on an assessment. So you want to make sure that you get to the point where you're comfortable doing this without checking it on your calculator. Okay, so your homework is 8 problems. And I know that sounds like quite a few. However, most of them should be really quick. Okay. So the first 4 are related to what we talked about in class. Okay. Transformations and families of functions. And then the last 4 are applying that specifically to the absolute value function like we just did in the video. Okay. So these 8, make sure you upload it to Blackbaud, and make sure when you're uploading it, you're always checking that when it uploads, your file is visible to me and not just a blank document. And a couple things that have been happening recently, if you try to upload it using your phone, it's not always going to work. And if you try using Safari or Firefox, that hasn't been working. So try it in Chrome. So you can do it your normal way, however you've been doing it. But if you're getting any error messages, or if your document is being submitted blank, try using Google Chrome on your computer. Okay, email me if you have any trouble, and I'll see you in class.